What if the greatest unexplored frontier on Earth has nothing to do with space? Right now, humanity possesses more detailed maps of Mars than we do of our own ocean floor. Entire Martian landscapes have been captured at resolutions down to a few meters. Meanwhile, vast regions of Earth's seabed remain known only as blurred outlines and educated guesses measured in kilometers. In some places, we know the moon's surface better than the terrain lying beneath the Pacific Ocean. Mars sits over 140 million miles away. The deep ocean begins just 2 miles beneath the waves. Yet one is charted with remarkable precision, while the other remains largely invisible. The reason is not distance. The reason is not funding. The reason is difficulty. Because the deep ocean is not simply another place on Earth. It is a world that actively resists being known, where human bodies cannot survive, where our most powerful tools fail, and where darkness, pressure, and silence combine into something closer to an alien environment than anything found on this planet's surface. To understand why it remains so hidden, we first need to understand just how vast and how genuinely unreachable it truly is. The ocean covers more than 70% of Earth's surface, but that single statistic hides a far more profound truth. If all ocean water disappeared tomorrow, what would emerge would not be empty basins or barren flatlands. What would emerge is a second geography of this planet, one as complex, as dramatic, and as varied as every continent combined. Mountain chains longer than any range on land, trenches deep enough to swallow Mount Everest whole and still have room above it, vast volcanic plains stretching for thousands of miles in complete darkness, continental fractures so enormous they would dwarf the Grand Canyon many times over. The longest mountain range on Earth is not the Andes. It is not the Rockies or the Himalayas. It is the mid-ocean ridge, a continuous volcanic system stretching roughly 65,000 kilometers around the planet, like a wound formed by Earth's own internal forces. A structure so massive it encircles the globe, and yet most Americans have never heard its name. And here is what makes this even more striking. Much of this terrain remains mapped at resolutions so coarse that entire mountains could still be hiding inside a single pixel of our best global models. Meanwhile, Mars has been surveyed by orbiting spacecraft using laser altimeters precise enough to detect elevation changes smaller than the height of a house. The surprising reality is this exploring space is sometimes easier than exploring Earth, because space allows us to see, the ocean does not. Darkness is only the beginning. Sunlight fades rapidly below the surface. By 200 meters, it has thinned to almost nothing. By 1,000 meters, it is gone entirely permanently and without exception. From that depth downward, the ocean exists in a darkness so complete that no natural light has touched it in billions of years. But darkness alone does not explain why this environment resists exploration the way it does. At 4,000 meters, pressure exceeds 400 times what the human body experiences on land. Materials that perform flawlessly at the surface begin to compress, fatigue, and fail. And at Challenger Deep, the lowest point on Earth, pressure reaches levels capable of collapsing steel structures that would survive almost any other environment on this planet. Yet even pressure is not the greatest obstacle. Radio waves cannot travel through seawater. That single physical fact changes everything. Every tool that makes modern exploration efficient satellites, remote sensing, real-time communication depends on electromagnetic signals moving freely through open space. Underwater, those signals die within meters of the surface. Instead, scientists must use sound. Ships send sonar pulses downward and wait for echoes to return from the seafloor below. Each pass produces only a narrow strip of mapped terrain. Building a complete picture requires crossing the ocean again and again, line by line, year after year. It is less like photographing a planet, and more like reading a book, one letter at a time. Humans evolved for light, air, and manageable pressure. The deep ocean removes all three simultaneously and completely. We cannot breathe there. We cannot see naturally. We cannot survive the pressure even for seconds without engineering protection that represents some of the most demanding design challenges in modern science. At extreme depths, failure is not gradual. There is no warning curve, no slow deterioration that allows time to react. There are only thresholds. And when those thresholds are crossed, the outcome is instantaneous. Unlike high-altitude environments where the human body can acclimate over days and weeks, the deep ocean offers no biological pathway for adaptation whatsoever. No amount of training prepares the human body for pressures that would crush it before a single breath could be drawn. We are visitors there, entirely dependent on machines. And those machines must function perfectly because rescue at these depths is nearly non-existent. In some scenarios, it would take days simply to reach a disabled vehicle on the seafloor, days during which survival would already be impossible. This is not an environment that punishes mistakes slowly. It punishes them immediately. And yet here is the fact that reframes everything. More people have walked on the surface of the moon than have descended into the deepest parts of our own ocean. Not because the ocean is farther, not because it is less scientifically valuable, but because it is less forgiving than anywhere else on Earth, and perhaps anywhere humans have ever attempted to go. In 1977, a team of scientists descended into the Galapagos Rift aboard a deep-sea submersible, expecting to find what most researchers assumed defined the deep ocean cold: barren darkness and very little else. What they found instead changed biology forever. Clustered around hydrothermal vents, fractures in the seafloor where superheated chemical-rich water pours directly from Earth's crust, were entire ecosystems. Dense, thriving, and completely alive. Giant tube worms, several feet long, anchored to rock. Blind shrimp moving through mineral-laden currents. Deep-sea fish navigating a world with no light and no connection to the surface above. There was no sunlight reaching this place, not a single photon. Yet life was everywhere. The discovery forced scientists to dismantle one of biology's most foundational assumptions, that all complex life ultimately depends on the sun. These ecosystems operated on an entirely different principle. Instead of photosynthesis, they ran on chemosynthesis. Microbes converted hydrogen sulfide pouring from the vents into usable energy, and those microbes became the foundation of entire food webs, operating in permanent darkness, miles beneath the surface. Life did not merely survive here, it built a complete world on entirely different rules, and the implications reached far beyond Earth itself. Some scientists now believe that similar chemosynthetic ecosystems may exist beneath the frozen, ice-covered oceans of Europa, one of Jupiter's moons, where liquid water almost certainly exists in permanent darkness, far from the sun. Meaning the deep ocean may not just teach us about life on this planet. It may teach us exactly where to look for life beyond it. Deep ocean creatures do not look strange because nature ran out of ideas. They look the way they do because they evolved under an entirely different set of rules than anything living at the surface. Some fish have developed transparent heads, fluid-filled domes through which their eyes rotate freely, tracking faint traces of bioluminescent light in otherwise total darkness. Some species produce cold light through chemical reactions more energy efficient than any illumination technology humans have yet engineered. Some crustaceans manufacture biological antifreeze proteins that prevent cellular damage in water cold enough to destroy surface organisms within minutes. And some microbes repair DNA damage in ways now being actively studied as potential pathways for cancer treatment. These are not curiosities. They are solutions, precise, elegant, and millions of years in the making. What drives this biological creativity is not abundance, it is scarcity. In the deep ocean, energy is the rarest resource of all. Food arrives slowly and in small quantities, drifting down from the world above. Many deep species grow at rates almost imperceptibly slow compared to their shallow water relatives. Others have reduced their metabolic rates to levels barely detectable by modern instruments, burning as little energy as biologically possible while still sustaining life. This is evolution shaped not by competition for speed, but by the discipline to endure. And these adaptations ripple outward into medicine, into materials science, and into our understanding of what life is truly capable of when pushed to the absolute edge of possibility. Most people think of the deep ocean as a place apart, remote, silent, and completely disconnected from the world they live in. That perception is fundamentally wrong. The deep ocean does not exist alongside the surface world, it sustains it. Cold, deep-water currents act as the planet's circulatory system, absorbing heat from the tropics and transporting it across entire hemispheres in ways that regulate temperature patterns on land, thousands of miles away. Without these currents, the climate systems that make large portions of Earth habitable would behave in ways we cannot fully predict. Carbon moves through the deep ocean in ways equally critical. When billions of tiny surface organisms die, they sink, carrying absorbed carbon downward through the water column in a slow, invisible process scientists call marine snow. That carbon settles into abyssal plains, where deep microbial communities process it over thousands of years, quietly regulating Earth's atmospheric chemistry long before humans existed to observe it. This single mechanism has been running continuously since before our species appeared, and it is still running now. But human activity is reaching even these depths. Deep-sea mining exploration, fishing pressures penetrating further than ever before. Climate change, altering temperatures and chemistry in waters that have remained stable for millennia, which creates a reality that is genuinely difficult to sit with. We are beginning to influence systems we barely understand. We are making decisions about environments we have barely mapped, and the consequences of those decisions may not surface in every sense of that word for generations to come. Consider this number carefully. Only about 1/4 of the global seafloor has been mapped using modern high-resolution sonar. 1/4. In the year 2024, with all the technology civilization has produced, 3/4 of our own planet's ocean floor remains essentially unknown. The rest relies largely on indirect satellite gravity measurements, instruments that detect the subtle pull of large underwater structures from orbit. These measurements can reveal the broad shape of a mountain range or a deep trench, but they cannot show what lies within. Smaller peaks, hidden valleys, underwater hazards that could threaten infrastructure or navigation, all of it remains invisible at that resolution. New seamounts are still being discovered. Underwater landslides, larger than entire cities, continue to be identified for the first time. Entire volcanic systems remain so poorly understood that scientists cannot yet determine whether they are active or dormant. The Seabed 2030 initiative was launched specifically to address this, an international effort aimed at producing a complete high-resolution map of the entire ocean floor before the end of this decade. But at current mapping speeds, the scale of what remains is almost difficult to comprehend. Some estimates have suggested that completing this map using traditional research vessels alone could take well over a century. And here is the irony that this timeline produces. Humanity may achieve complete maps of Mars, the Moon, and multiple asteroids before finishing the map of the planet we actually live on. The world beneath our own ocean, closer than any destination we have ever launched a rocket toward, may be the last place on Earth we finally come to know. Surface life moves to the rhythm of seasons, temperature shifts, daylight cycles, weather patterns that change week to week and year to year. These forces push evolution forward at a pace shaped by constant environmental pressure and continuous biological competition. The deep ocean operates on an entirely different clock. Many regions of the seafloor have remained thermally and chemically stable for thousands of years, some for far longer. No seasons reach them, no storms disturb them, no cycles of light and darkness drive their rhythms. In these places, the pressures that accelerate surface evolution simply do not exist in the same form, and life responds accordingly. Some deep species show remarkably slow rates of genetic change across generations. Others evolve extreme specialization, so precise and so narrow that they exist in ecological niches measured in meters rather than miles. Some lineages appear to persist with almost no visible change across geological periods that dwarf the entire history of human civilization. Studying these organisms gives scientists something extraordinarily rare, a window into biological resilience at its most fundamental level. How life survives mass extinction events. How ecosystems rebuild themselves after catastrophic collapse. How living systems maintain continuity across timescales that make human history feel like a single afternoon. These are not abstract scientific questions. As environmental pressures accelerate across the planet today, these questions are becoming urgently practical. Understanding how life endures extreme instability may prove to be among the most important knowledge the deep ocean has left to offer, and we are only beginning to ask it the right questions. Ocean mapping is easy to frame as exploration, as adventure, as the romantic pursuit of unknown territory for its own sake. But the practical reality reaches far deeper than that. More than 95% of all international data, every email, every financial transaction, every streaming signal, every piece of digital communication crossing between continents travels through fiber optic cables resting silently on the seafloor. These cables are among the most critical infrastructure on Earth, and accurate seafloor maps are essential to protecting them, to routing them safely, to understanding the geological hazards that could damage or sever them without warning. Seafloor data directly improves earthquake models used to predict where seismic events will occur and how severe they will be. It refines tsunami warning systems that protect millions of people living in coastal communities across the Pacific and Indian Oceans. It guides shipping routes through waters where uncharted seamounts and ridges represent real navigational hazards to vessels carrying global trade. And it feeds the climate models that governments and scientists rely on to understand how Earth's systems are changing, because those models are only as accurate as the ocean data that underlies them. This is not exploration in the romantic sense. It is foundational science, the kind of quiet, essential knowledge that modern civilization depends on without ever fully acknowledging the debt. Every gap in the seafloor map is not just an unanswered scientific question. It is a gap in the infrastructure of human understanding itself. And the more precisely we map what lies beneath, the more clearly we realize how much our world above depends on a place most people will never see. So why have we mapped Mars better than our own ocean floor? The answer is not negligence. It is not a failure of curiosity or a misallocation of scientific ambition. The answer is something more fundamental than any of those things. Mars allows observation from above. The ocean demands entry from within. Space is empty. Signals travel freely across hundreds of millions of miles and arrive with enough clarity to build precise topographic models of entire planets. The ocean is dense, chemically complex, and physically hostile to every sensing technology we rely on. What works effortlessly in the vacuum of space fails completely 2 miles beneath the waves. Orbital spacecraft can scan entire continents in a single day. A research vessel mapping the seafloor with sonar produces a strip of terrain, perhaps a few kilometers wide, and then must turn around and do it again. And again. For years. Exploration has never been defined by distance alone. It is defined by how difficult a place is to observe, by how resistant an environment is to the tools we bring to it, and by how completely it forces us to abandon the methods that work everywhere else. The hardest frontier is not always the one farthest away. Sometimes it is the one hidden in plain sight, lying beneath an ocean we have sailed across for thousands of years without ever truly seeing what was below us. And that may be the most quietly humbling realization in all of science. There is a quiet humility in what the deep ocean asks of us. Humanity can image galaxies billions of light years away. We can detect planets orbiting distant stars by measuring the faintest dimming of their light. We can map the surface of worlds we may never visit and send machines to the edges of our solar system that are still transmitting signals back to Earth decades later. And yet much of our own planet remains unseen. Not because we lack the intelligence to look, not because the technology does not exist, but because nature still sets limits that ambition alone cannot overcome. The deep ocean does not yield to impatience. It does not reward shortcuts. It requires something that modern science does not always have in abundance: time, persistence, and a genuine willingness to sit with how much remains unknown. Discovery does not always require rockets. Sometimes it requires descending slowly into darkness with nothing but instruments and questions. Sometimes it requires decades of narrow sonar strips assembled one pass at a time. And sometimes it simply requires the intellectual honesty to admit that the most familiar planet in the universe still holds secrets we have not yet earned the right to see. If you are drawn to the science of Earth's last unexplored frontiers, Sunken Realms Deep is where that story lives. The hidden geography, the extraordinary biology, and the quiet physics of a world beneath the waves, where some of the greatest scientific discoveries of this century are still waiting. Because the greatest unknown places on Earth are not always distant. Sometimes they are simply deeper than we ever thought to look.